lot of undergrad students that we deal with know answers, and they try to work during the undergrad. They try to learn answers, right? So how important is to learn a tool without understanding the background, or so both Procast and Answers have a background of FEA. How important is to understand FEA to uh, to analyze these two
Yeah,
results? How,
I
what
would
do,
say
what's your
I would
thoughts?
say it's quite important, to be honest. It's really important, simply because sometimes finite elements almost looks like a black box. So you draw a CAD model, you enter some boundary conditions, you hit run, or maybe you mesh, and then you hit run, and then on the other hand, you get just the contour plot, which looks really nice. But how can I trust this contour plot? It looks very colorful. It's perfect. I can, with a click of a button, jump from a displacement to a strain to a stress. But you know, where's the physics behind the transition from the CAD model that I inputted at the beginning and the contour plot that I get at the end? So I feel like understanding what's happening behind the scenes is really important, because quite often, sometimes maybe you select the wrong element, and that element takes into account some assumptions.
Mm-hmm.
For example, it ignores thickness, or it models everything as a 2D plane stress problem when yours is a 3D. So you will still get an answer, but the answer is wrong. So it is quite important to actually know the physics behind it, and not just the theory behind finite elements. I would say also the solid mechanics theory behind it. So if I'm using, let's say, a beam element, how is that different from a shell element? What are the different, let's say, degrees of freedom that are constrained here that are not constrained there? If I'm modeling, let's say, a spherical vessel, is it okay to use shell elements, or no, should I use plate elements?
Mm-hmm.
So it's really, even for me, like, for example, I've never used Procast before, but now that I have to use it, I have to go through the elements that Procast has and look at the kind of the physics behind every element, so that I know that the element that I'm selecting is actually exactly modeling what I have, and it's not taking into account some assumptions that will actually damage my model. So long story short, yeah, it's really important to know not just the finite element theory, but also the physics used in the finite elements. So the boundary conditions, the degrees of freedom constraints, and so on.
Okay. And you use MATLAB to kind of validate your approach. Is that what you use MATLAB for?
I would say not exactly to validate. It depends on the project. For me, like, MATLAB is mostly a computational tool. Like, it speeds things up. If I'm running a lot of iteration, different scenarios, I use MATLAB. If I'm doing some design optimization, I use MATLAB. They have really powerful toolboxes for that. But for instance, at this stage, like, I'm not using MATLAB when it comes to finite elements or doing modeling itself. So I'm not writing my own code in MATLAB to solve some problems. So, but I still use it. Let's say I want to minimize a certain function with some constraints. So that's pretty much a math problem that was derived from something solid mechanics, but now it's simply a math problem. There's an objective function, and there's a constraint, mm-hmm. and I need to solve it. So that's when I use MATLAB mostly.
Okay, great. So speaking about math,
Yep.
here's another lead in. Many students that we talk feel the math they learn in undergrad is not directly is not applicable when they go to grad school, or at least go to the
Yeah.
industry. So what do you think about math and its applications, and
Yeah.
how it helps? What are your thoughts?
It is it's a tricky topic. Like, I hear this comment all the time, and kind of students sometimes complain, like, where am I going to see this? Why is this necessary? And you even get these comments from good students studying engineering. So it's not just for people who are not interested in sciences. But I feel like, down the road, like, students will encounter, I would say, let's first start with courses. They will encounter courses down the road that will require a strong background in mathematics. For example, right now I'm teaching system dynamics. And anytime you're solving a system dynamics problem, you need to use Laplace transform. So it's a pure mathematical concept, okay, to transition from a time domain to some other algebraic domain to help you solve a partial differential equation. So if you think about it, the sentence that I said, it's pure math. Now I'm applying it to a differential equation that, yes, came from an equation of motion or came from Newton's second law or came from energy methods. So the source is always, there's a physics there. You get the equation, but now the physics stops there. It gave you the equation. Now it's math's job to solve this equation. And that's where math is important. So, and quite often, it's easier to get the equation. I get there, but how do I solve it? And that's where math is involved, whether it's solving partial differential equations, linearizing systems, using Laplace transform, and so on. So I totally understand that it's hard for, especially, let's say, first or second year students to kind of understand that or grasp the idea of math being important. But, they have to trust the system. So math has been there for quite some time, and it's there for a reason. So it's not just there as an extra course or an elective. No, it's there for a reason. They will end up using it down the road. Sometimes even if it's not a direct use of what you learned, but now that you've learned it, it's in your head, and you have the capacity to think in a certain way. So maybe it's very hard to find an example where, yes, I used, I don't know, Gaussian elimination. I don't remember the last time I used it, but the logic behind it, or Newton-Raphson method, or bisection method. So yeah, I don't remember the last time myself I used it, but I know how to use it, and I know the logic behind it, and that makes me a better engineer because it helps me think better. So if I'm encountering it, maybe it could be a different problem, but I have the tools in my head to approach this problem because of the background that I have in mathematics.